Hello there, and welcome to the Sleepy Library, where we explore the world's most fascinating science through stories designed to help you rest. Tonight, we travel to the most extreme corners of our planet, places where temperature becomes something almost beyond human comprehension. We'll visit landscapes so hot they shimmer like mirages, and valleys so cold that breathing feels like swallowing knives of ice. Close your eyes, settle deeper into your pillow, and let your mind wander with me to Earth's temperature extremes. Our planet is a study in contrasts, a sphere spinning through space where one region can bake under relentless sunshine, while another shivers in endless darkness. Between these extremes exists the comfortable middle, where most of us live, where temperatures allow water to flow liquid through rivers, where plants grow green and abundant, where the air feels gentle against our skin. But tonight, we venture beyond that comfortable middle. We seek the edges, the boundaries, the places where Earth itself seems to test the limits of what matter and life can endure. Imagine for a moment the full spectrum of temperatures that exist naturally on our world. From the blistering heat of sun-scorched deserts to the crystalline cold of Antarctic ice, our planet spans a range so vast that the human body can only tolerate a tiny sliver of it. We evolved in a narrow band of comfort, typically thriving between about 15 and 25 degrees Celsius. Step outside this range for long, and discomfort turns to danger. Venture far enough toward either extreme, and survival becomes a matter of minutes or even seconds. Yet Earth, in its infinite creativity, has carved out places where these extremes persist year after year, century after century. Some of these places are so hostile that they remain almost untouched by human presence. Vast expanses where only the hardiest microorganisms cling to existence. Others, remarkably, have become home to human communities. People who have adapted their entire way of life around temperatures that would send most of us fleeing in terror or seeking shelter with desperate urgency. Tonight's journey will take us across continents and climates. We'll stand in valleys where the ground itself seems to melt with heat, where the air warps and bends light into strange mirages that deceive the eye. We'll venture onto ice sheets so vast and so cold that they hold within them a record of Earth's atmosphere stretching back hundreds of thousands of years. Each layer of ice, a page in the planet's climate history. We'll meet the people who have chosen to inhabit these extreme environments, and we'll try to understand what drives the temperature differences that make one place a furnace and another a freezer. Temperature is such a simple concept until you really think about it. It's just the movement of molecules, the dance of atoms vibrating faster when hot, slower when cold. Yet this simple phenomenon shapes everything about our world. It determines where ice forms and where deserts spread. It guides ocean currents and atmospheric winds. It decides which creatures can survive where and which places remain empty of life. Temperature is the invisible hand that sculpts landscapes, carves valleys, and builds mountains of ice. At the molecular level, temperature is kinetic energy. The atoms and molecules that make up all matter are constantly in motion, vibrating, rotating, colliding with their neighbors. When we say something is hot, we mean these particles are moving quickly, bouncing around with high energy. When we say something is cold, the particles are moving more slowly, with less kinetic energy. At absolute zero, the theoretical coldest possible temperature of -273.15 degrees Celsius, all atomic motion would cease. Of course, this temperature cannot actually be reached due to the laws of quantum mechanics. But scientists have come remarkably close in laboratory settings. The story of Earth's hottest and coldest places is really a story about energy. Where does heat come from, and where does it go? Our planet receives nearly all its warmth from the sun, that glowing furnace 93 million miles away. The sun is powered by nuclear fusion, where hydrogen atoms merge to form helium, releasing tremendous amounts of energy in the process. This energy radiates outward in all directions, and a tiny fraction of it reaches Earth approximately 8 minutes after leaving the sun's surface. Solar radiation travels through the vacuum of space as electromagnetic waves, moving at the speed of light. When these waves strike Earth's atmosphere, several things happen. Some energy is reflected back into space by clouds, ice, and other bright surfaces. Some is absorbed by gases in the atmosphere, particularly ozone in the stratosphere, which absorbs ultraviolet radiation and protects life below from harmful UV rays. And much of the energy passes through the atmosphere to strike the surface, where it is absorbed by soil, rock, water, and vegetation. But the sun doesn't illuminate Earth evenly. The planet is a sphere, which means sunlight strikes the equator at a nearly perpendicular angle, concentrating energy in a small area. At higher latitudes, toward the poles, sunlight arrives at increasingly oblique angles, spreading the same amount of energy over a larger area. This is why tropical regions are generally warm and polar regions are generally cold. It's simple geometry, but it has profound consequences for climate, weather, and the distribution of life on Earth. The angle of sunlight also changes with the seasons. Earth's axis is tilted by approximately 23.5 degrees relative to its orbital plane around the Sun. This tilt means that during summer in the northern hemisphere, the northern half of the planet is angled toward the Sun, receiving more direct sunlight and experiencing longer days. Meanwhile, the southern hemisphere experiences winter, with less direct sunlight and shorter days. 6 months later, the situation reverses. This axial tilt is why we have seasons, and it creates additional complexity in Earth's temperature patterns. But sunlight alone doesn't determine temperature at any given location. Many other factors come into play. Altitude matters tremendously. The atmosphere is thickest at sea level and thins rapidly with elevation. Thinner air holds less heat, which is why mountain peaks are cold even at the equator. For every 1,000 meters of elevation gain, temperature typically drops by about 6 to 10 degrees Celsius, depending on humidity and other factors. This is why you can find snow-capped mountains in tropical countries, glaciers persisting year-round just a few degrees from the equator. Proximity to water also plays a huge role. Water has an extraordinarily high heat capacity, meaning it can absorb or release large amounts of heat with only small changes in temperature. Oceans act as thermal buffers, moderating temperatures in coastal areas. Cities near the ocean experience milder winters and cooler summers compared to inland cities at the same latitude. Conversely, places far from any large body of water tend to have more extreme temperature swings, with hotter summers and colder winters. This is called continentality, and it's one reason why the interior of large landmasses like Asia experiences such dramatic seasonal temperature variations. Humidity affects how hot or cold we feel. In humid air, sweat evaporates slowly, making it harder for our bodies to cool down. This is why humid heat feels more oppressive than dry heat, even at the same temperature. The heat index, which factors in both temperature and humidity, gives a better sense of how conditions feel to humans than temperature alone. Similarly, in cold conditions, humid air conducts heat away from our bodies more efficiently than dry air, making humid cold feel more penetrating than dry cold. Wind also influences how we experience temperature. Moving air strips away the thin layer of warm air that forms around our skin, exposing us to the full ambient temperature. This is why weather forecasts include wind chill in winter, indicating how cold it feels when wind is factored in. On a calm day, you might be comfortable at -5 degrees Celsius wearing a good jacket. But with strong wind, the same temperature can feel brutally cold, and exposed skin can develop frostbite in minutes. Cloud cover makes an enormous difference too. Clouds act like a blanket, trapping heat radiated from Earth's surface and keeping nighttime temperatures warmer. Clear skies allow heat to escape freely into space, leading to colder nights. This is why desert areas, which tend to have clear skies, often experience dramatic temperature swings between day and night. The same location that bakes at 50 degrees during the afternoon might cool to near freezing by dawn. The color and texture of the ground surface also matter. Dark surfaces absorb more solar radiation than light surfaces, a property called albedo. Fresh snow reflects up to 90% of incoming sunlight, which is why snow-covered areas stay cold even in bright sunshine. Dark soil, rock, or vegetation absorbs much more energy, leading to higher surface temperatures. This is why parking lots and dark-roofed buildings contribute to urban heat islands, where cities become notably warmer than surrounding countryside. Vegetation affects temperature in multiple ways. Plants absorb water through their roots and release it through their leaves in a process called transpiration. This evaporation cools the air around the plants, much like sweating cools our bodies. Forests can be several degrees cooler than nearby open areas during hot weather. Trees also provide shade, blocking direct sunlight from heating the ground. The removal of vegetation, whether through deforestation, overgrazing, or natural processes, can lead to higher local temperatures and can even influence regional climate patterns. All these factors interact in complex ways to create Earth's diverse temperature zones. The hottest places on our planet tend to be low-lying deserts far from oceans, with dark-colored surfaces, clear skies, and dry air. The coldest places are high-altitude or high-latitude locations, often on ice-covered landmasses, far from moderating ocean influences, experiencing long periods without sunlight. Understanding why these extremes occur requires looking at the specific geography, geology, and atmospheric conditions of each location. Let us begin our journey in the scorching realm of heat, where the sun's energy concentrates with such intensity that the very ground beneath your feet becomes almost too hot to imagine. We'll travel first to a desert in Iran, then to valleys in North America, then to places scattered across Earth's arid zones, where heat has become the defining feature of existence. As we explore each location, pay attention to how the factors we've discussed combine to create these extreme conditions. In the southeastern corner of Iran lies a vast expanse of sand and rock known as the Lut Desert, or Dasht-i-Lut in Persian. The name itself speaks volumes, for Lut means emptiness, bareness, land stripped of water and life. And Dasht simply means plain. Together, they describe exactly what this place is: a plain of emptiness. A landscape so harsh that for centuries it existed primarily in stories told by travelers who dared to cross it. The Lut Desert stretches across an area larger than some small countries, covering approximately 51,800 square kilometers. To put that in perspective, Imagine an area about the size of Costa Rica, filled almost entirely with sand dunes, salt flats, and formations of wind-carved rock. This is Iran's contribution to the great belt of deserts that extends from the Atlantic coast of Africa all the way to Mongolia, a ribbon of aridity wrapping around a significant portion of our planet. This desert belt exists because of global atmospheric circulation patterns. Warm, moist air rises at the equator, where intense solar heating makes the air buoyant. As this air rises, it cools and loses its moisture, which falls as rain in tropical regions. The now dry air spreads north and south at high altitude, gradually cooling and eventually sinking back toward the surface, around 30 degrees latitude in both hemispheres. This sinking air is compressed as it descends, which warms it and makes it extremely dry. Most of the world's great deserts, including the Sahara, the Arabian Desert, the deserts of Iran and Central Asia, and the deserts of the southwestern United States, lie in these subtropical high-pressure zones created by this global circulation pattern. The Lut Desert occupies a particularly unfortunate position in this system. Not only does it sit in the subtropical high-pressure belt, but it's also locked behind mountain barriers that block any moisture that might arrive from the ocean. To the west lie the Zagros Mountains, and to the north and east are other mountain ranges. These peaks intercept moisture-bearing winds, forcing the air to rise and cool, which causes precipitation to fall on the windward slopes. By the time the air descends into the Lut Basin, it has been wrung dry of moisture. What makes the Lut Desert extraordinary is not just its size or its emptiness, but its heat. Scientists, using satellites to measure Earth's surface temperature, have consistently found that the Lut Desert reaches temperatures higher than almost anywhere else on the planet. Between the years 2003 and 2010, NASA's Aqua satellite, equipped with a device called the Moderate Resolution Imaging Spectroradiometer, scanned the surface of our planet continuously. Year after year, the highest temperatures recorded came from the Lut Desert. In the summer of 2005, the satellite measured a surface temperature of 70.7 degrees Celsius in the Lut Desert. That's 159.3 degrees Fahrenheit. More recent data, analyzed in 2019, found even higher readings, with some spots reaching 80.8 degrees Celsius, which is 177.4 degrees Fahrenheit. To put this in perspective, water boils at 100 degrees Celsius. The hottest spots in the Lut Desert reach temperatures more than 3/4 of the way to the boiling point of water. Imagine a temperature so extreme that if you placed an egg on certain rocks in the Lut Desert on a summer afternoon, it might actually cook, slowly but surely, from the radiant heat of the stone. But here's something important to understand. These satellite measurements record the temperature of the ground surface itself, not the air above it. Air temperature and surface temperature can differ dramatically. While the rocks and sand of the Lut Desert might reach 80 degrees Celsius, the air temperature measured at human height, about 5 feet above the ground, would be significantly cooler. Still scorching hot by any standard, perhaps hovering around 50 to 55 degrees Celsius on the hottest days, but not quite as extreme as the ground itself. This distinction matters because when we talk about record temperatures, we need to specify whether we're measuring air temperature or surface temperature. They're related, but different measurements. The difference between surface and air temperature is due to how heat moves through the atmosphere. The ground absorbs solar radiation and gets very hot. This heat is transferred to the air directly above the surface through conduction, and also through infrared radiation that the hot ground emits. But air is not a particularly good conductor of heat, and it can move, carrying heat away through convection. So, while the surface might be extremely hot, the air a few feet above it is somewhat cooler, having been stirred and mixed with air from other areas by wind and convection currents. Why does the Lut Desert get so hot? Geography and geology conspire to create this furnace. The desert sits in an interior basin, surrounded by mountains. These mountains act like the rim of a bowl, trapping hot air inside and preventing cooler winds from entering. This is called a rain shadow. Moisture-laden air approaching from the ocean never makes it over the mountain barriers. As air rises to cross the peaks, it cools and releases its moisture on the windward side, leaving the interior basin dry and parched. The Lut Desert is a hyper-arid environment, meaning it receives almost no rainfall. Most areas see less than 30 millimeters of precipitation per year, and some sections go years without a single drop. To put this in context, a typical tropical rainforest receives over 2,000 millimeters of rain per year. Even cities in relatively dry climates usually get at least 300 to 500 millimeters. The Lut Desert receives perhaps 1% of that. It's not just dry, it's profoundly, almost incomprehensibly dry. Without water to evaporate and cool the air, without vegetation to provide shade and transpiration, the sun's energy has nowhere to go but into heating the ground. The surface here consists of dark rocks, salt flats, and densely packed sand. Dark surfaces absorb more solar radiation than light surfaces, and the Lut's terrain is particularly effective at soaking up heat. The desert floor in many areas is covered with dark pebbles and closely packed rock fragments, sometimes called desert pavement. These rocks have been weathered and oxidized over millennia, developing dark surface coatings that absorb sunlight very efficiently. The Lut Desert features several distinct regions, each with its own character. In the western part of the desert, find the Yardangs, massive ridges carved by wind erosion. Between June and October each year, strong winds blow across the region from the northwest. These winds, driven by pressure differences in the atmosphere, can reach remarkable speeds. They pick up sand particles and hurl them across the landscape like tiny projectiles, sandblasting the bedrock and creating massive ridges called Yardangs. These are corrugated formations, parallel ridges carved by wind over thousands of years. Some of the Yardangs in the Lut Desert are so large and striking that they can be seen from space, looking like massive fingerprints pressed into the earth. Walking among the Yardangs would be like navigating a maze of stone walls. The ridges run parallel to the prevailing wind, separated by deep troughs. In places, these formations stand 30 or even 50 meters high, towering cliff-like structures of eroded rock. The wind has carved the softer layers more deeply than the harder layers, creating overhangs and bizarre shapes that seem almost architectural in their complexity. Local legends tell of travelers who entered the Yardangs and became lost, unable to find their way out of the labyrinth of stone. In the central part of the Lut Desert lie vast expanses of coluts, which are another form of wind-carved landform. These are massive mesas and pedestals of rock, sculpted into fantastic shapes by the relentless wind. From a distance, coluts can look like a ruined city, with towers and walls and structures that seem almost artificial. Up close, you can see the layers of different sedimentary rocks, each eroding at slightly different rates, creating the stepped appearance of these formations. The interplay of light and shadow on the coluts throughout the day creates an ever-changing landscape, particularly beautiful in the hours around sunrise and sunset, when the low-angle sunlight emphasizes every ridge and hollow. The eastern portion of the Lut Desert features some of the tallest sand dunes in the world. These golden mountains of sand can reach heights of 300 meters, taller than many hills and even some mountains. Standing at the base of these dunes and looking up is a humbling experience. The sand appears to flow like frozen waves, ripples and curves sculpted by wind into endlessly varied patterns. Each grain of sand has been carried by the wind, bouncing and rolling across the desert surface in a process called saltation. Over time, countless billions of these tiny journeys have built dunes of impressive size and complex geometry. The sand dunes of the Lut are not static. They move, slowly but constantly, driven by the prevailing winds. A large dune might migrate several meters per year, with sand grains carried up the gentle windward slope, then tumbling down the steep leeward face. This creates the characteristic sharp crest and steep face that you see on most large dunes. In the height of summer, these dunes radiate heat like furnaces, the air above them shimmering with thermal distortion. If you were to climb one of these dunes on a hot afternoon, each step would sink into sand so hot that it would burn through the soles of your shoes within minutes. Between the dunes and the yardangs and the kaluts, there are also vast salt flats in the Lut Desert. These are ancient lake beds, dry now for thousands of years, covered with layers of salt and other minerals left behind as the water evaporated. The salt flats are stark and bright, reflecting sunlight intensely. They're also remarkably flat, stretching for kilometers without significant variation in elevation. The surface is often broken into polygonal patterns, created by the expansion and contraction of the salt crust as temperatures change. During the rare occasions when rain falls, these flats can become temporarily flooded, creating shallow lakes that last for days or weeks before evaporating once again. Despite its harsh reputation, the Lut Desert is not entirely lifeless. Scientists have found communities of bacteria and other microorganisms that have adapted to survive in these extreme conditions. These extremophiles, as they're called, have evolved remarkable adaptations. Some can survive in a dormant state for years when conditions are too harsh, then quickly become active when tiny amounts of moisture become available. Others have protective proteins that prevent their cellular machinery from being damaged by extreme heat. Studying these organisms helps scientists understand the limits of life on Earth and gives clues about where we might find life on other planets. Insects, specially evolved for the heat, make their homes here, including species found nowhere else on Earth. The Lut cockroach can survive on surfaces that reach 70 degrees Celsius, an adaptation that seems almost impossible, yet exists. These insects are typically most active during the brief, cooler periods of dawn and dusk. They've developed behavioral strategies, like spending the hottest hours buried beneath the sand, where temperatures are slightly lower, and physiological adaptations, like the ability to tolerate significant water loss without harm. Some desert insects can lose up to half their body weight in water and still survive, rehydrating quickly when moisture becomes available. There are also occasional plants in the Lut, though they're sparse and widely scattered. These plants cluster around areas where underground water comes close enough to the surface for roots to reach it, or, in the rare wadis, dry riverbeds that carry water briefly after the infrequent rains. Desert plants in the Lut have evolved remarkable strategies for water conservation. Many have very small leaves, or no leaves at all, conducting photosynthesis in their stems instead. Some have waxy coatings that reduce water loss. Others have extremely deep root systems, reaching down 10 or even 20 meters to find moisture. A few plants have seeds that can remain dormant in the soil for years or even decades, only germinating when rare rainfall provides enough moisture to support growth. The few animals that survive in the Lut are equally well adapted. Small reptiles, particularly lizards, are among the most successful vertebrates here. They're cold-blooded, which means they don't waste energy maintaining a constant body temperature. They can allow their body temperature to rise and fall with their environment, though they carefully regulate it through behavior, moving between sun and shade, burrowing into sand, and adjusting their activity patterns. Small rodents, mostly nocturnal, also inhabit the loot. They spend the brutal day hours in underground burrows, emerging only at night to forage for seeds and plant material. These animals have concentrated urine and very dry feces, minimizing water loss. Some can go their entire lives without drinking, getting all the water they need from their food. The Loot Desert has been designated a UNESCO World Heritage Site, recognized for its exceptional geological and aesthetic value. Visitors who travel there during the cooler months of late autumn and winter describe a landscape of surreal beauty. The colors shift from golden yellows to deep ochres to stark whites where salt deposits accumulate. The silence is profound, broken only by the whisper of wind across sand. In places far from any human settlement, you can experience silence of a quality that's almost impossible to find in the modern world. No traffic noise, no aircraft, no human voices. Just the occasional sound of wind and the rare call of a bird. The night sky over the Loot Desert, far from any cities, reveals stars in such abundance that the Milky Way appears as a glowing river across the heavens. The dry, clear air and lack of light pollution make this one of the best places on Earth for stargazing. On a moonless night, you can see thousands of stars with the naked eye, far more than most people ever witness in their lifetime. The sight of the Milky Way arching across the sky, so thick with stars that it looks like a cloud, is a reminder of our place in the cosmos, a humbling and beautiful experience. But the Loot Desert is not alone in its claim to extreme heat. Let us travel now across continents to North America, to a place that has captured the imagination of travelers and scientists alike for over a century. Death Valley, located in Eastern California in the United States, is a name that needs no elaboration. It tells you everything you need to know with just 2 words. This is a place where nature seems hostile to life, where the landscape itself appears sculpted by forces determined to make survival as difficult as possible. And yet, Death Valley is also strikingly beautiful, a contradiction that makes it one of the most visited national parks in America. Over 1 million people visit Death Valley each year, drawn by its dramatic landscape, its extreme reputation, and the strange allure of experiencing one of Earth's most hostile environments from the relative safety of an air-conditioned vehicle. The valley gets its ominous name from a tragic incident in the winter of 1849, when a group of pioneers became lost while attempting to find a shortcut to California's gold fields. The group, known to history as the Lost 49ers, entered the valley and became trapped by the surrounding mountains. Several members passed away before the survivors finally found a way out. As they left the valley, one member looked back and reportedly said, "Goodbye, ending place," and the name stuck. It's worth noting that this tragedy occurred in winter, when Death Valley's temperatures are actually quite pleasant. In summer, the pioneers likely would not have survived at all. The lowest point in North America sits within Death Valley, a location called Badwater Basin that lies 282 feet below sea level. The basin is covered with salt flats, white hexagonal patterns of salt crystals that stretch to the horizon like a bizarre honeycomb. These hexagons, each a few feet across, form because of the expansion and contraction of the salt crust as temperatures and moisture levels change. When rare rainstorms occur, a thin sheet of water covers these flats, creating what looks like an enormous mirror reflecting the sky and the surrounding mountains. But such events are fleeting. The water evaporates quickly under the intense sun and low humidity, leaving behind only salt and silence. The salt in Badwater Basin is not from the ocean. Instead, it's the result of thousands of years of mineral accumulation. Rain and snowmelt from the surrounding mountains carries dissolved minerals down into the valley. Because Death Valley is a closed basin, there's no outlet for this water. It can only evaporate, leaving the minerals behind. Over time, the concentration of salts and other minerals has built up, creating the thick deposits we see today. The salt is mostly sodium chloride, the same as table salt, but it's mixed with other minerals that give it varied colors, from pure white to beige to pink, depending on the mineral content. Standing at Badwater Basin on a summer day is an experience unlike any other. The flat, white expanse stretches in every direction, broken only by the dark mountain ranges that rim the valley. The air shimmers with heat, creating mirages that make distant mountains appear to float and distant objects seem closer or farther than they really are. The salt crunches under your feet, and the brightness of the reflected sunlight is almost painful, requiring sunglasses for comfort. The temperature can be so extreme that exposed metal surfaces become too hot to touch within minutes of being in direct sunlight. On July 10, 1913, a weather station at Furnace Creek in Death Valley recorded an air temperature of 56.7 degrees Celsius, which is 134 degrees Fahrenheit. This reading has stood for over a century as the highest officially recorded air temperature on Earth. The measurement was taken according to standard procedures, with the thermometer placed in a ventilated shelter approximately 5 feet above the ground, protected from direct sunlight, but allowing air to circulate freely around the instrument. This standardization is important because it ensures that measurements from different locations can be fairly compared. However, this record has been questioned by meteorologists in recent years. Some researchers, analyzing historical weather patterns and comparing temperatures recorded at nearby stations, have suggested that the 1913 reading might have been erroneous. They point out several anomalies. First, subsequent years, even with global warming causing temperature increases, have not produced readings anywhere close to that extreme. The hottest authenticated temperature in Death Valley in recent decades has been around 54.4 degrees Celsius, measured in August 2020 and July 2021. Second, analysis of temperatures at surrounding weather stations on that same day in July 1913 doesn't show the pattern you'd expect if Death Valley had genuinely been that hot. Nearby areas would have been experiencing near-record heat as well, but they weren't. One theory is that the thermometer was misread, or that it was measuring in an unrepresentative location. Historical photographs suggest that the weather shelter may have been moved at some point from its original position near an irrigated alfalfa field to a location above bare, dark ground, which would naturally be hotter. Another theory is that a localized dust storm or other unusual meteorological event created temporary extreme conditions right at the measurement site. We may never know for certain what happened that day, but the controversy highlights the importance of careful, standardized measurements and the value of having multiple nearby stations to cross-check unusual readings. Whether the 1913 record is valid or not, Death Valley remains undeniably one of the hottest places on Earth. During the summer months, from May through September, daily high temperatures frequently exceed 45 degrees Celsius, which is 113 degrees Fahrenheit. The valley holds the record for the longest stretch of consecutive days above 125 degrees Fahrenheit, a scorching spell that lasted for 10 days in July 1913. Imagine trying to exist in such heat, day after day, with no relief. Even at night during summer, temperatures rarely drop below 30 degrees Celsius. The rock and sand heated during the day continue to radiate warmth throughout the night, keeping the air hot. The monthly average temperature in Death Valley for July is around 47 degrees Celsius, making it the hottest month on average anywhere in North America. In comparison, most cities in the United States see July averages of 20 to 30 degrees, and even desert cities like Phoenix typically average around 35 degrees. Death Valley's average is more than 10 degrees hotter than these already warm locations, a difference that represents a fundamentally different order of heat. Why is Death Valley so hot? The answer involves several factors working together in perfect coordination to create extreme conditions. First, like the Lute Desert, Death Valley sits in a deep basin surrounded by mountains. The valley is long and narrow, running roughly north to south for about 200 kilometers, with the Panamint Range to the west and the Amargosa Range to the east. These mountains trap air inside the valley and prevent cooling winds from entering. The valley floor sits well below sea level in many places, while the surrounding peaks reach 3,000 meters or more in elevation. This creates a natural bowl that captures and holds heat. As the sun heats the ground, the hot air naturally rises due to its lower density. Normally, this hot air would rise high into the atmosphere and disperse. But in Death Valley, the rising air is blocked by the topography. It rises until it encounters cooler, denser air above. Then it stops rising and starts to spread horizontally. Eventually, it cools slightly and begins to sink back down. But as it sinks, it compresses, and compressed air warms. So the air that sinks back into the valley arrives warmer than when it left. This creates a feedback loop where the same air mass keeps getting heated over and over, with temperatures climbing higher each cycle. This process is called adiabatic heating, and it's one of the key reasons Death Valley gets so extraordinarily hot. Second, Death Valley's low elevation means the air pressure there is higher than at surrounding areas. At higher elevations, the atmosphere is thinner and pressure is lower. Air molecules are more spread out. At lower elevations, especially below sea level, the atmosphere is denser and pressure is higher. Air molecules are packed more closely together. This denser air can hold more heat energy, and the compression itself generates warmth. Think of it like compressing a gas in a cylinder. As you compress it, it gets warmer. The air in Death Valley is being compressed simply by the weight of the atmosphere above it, and this compression contributes to the high temperatures. Third, the valley is extremely dry. The mountains to the west, particularly the Sierra Nevada, block moisture-bearing winds from the Pacific Ocean. Storms approaching from the west drop their rain on the western slopes of the Sierra Nevada, which is why that region gets significant precipitation and has lush forests. By the time the air crosses the mountains and descends into the Great Basin, and eventually into Death Valley, it has been thoroughly dried out. Death Valley receives an average of only about 50 millimeters of rain per year, making it one of the driest places in North America. Some years see even less, and there have been years with essentially no measurable precipitation at all. Without moisture to absorb heat through evaporation, all of the sun's energy goes directly into heating the ground and air. Evaporative cooling is a powerful effect. When water evaporates, it absorbs a large amount of heat energy, which cools the surroundings. This is why sweating cools our bodies, and why coastal areas and regions with vegetation tend to be cooler than barren deserts. But in Death Valley, there's almost no water to evaporate, so this cooling mechanism is essentially absent. The soil and rocks in Death Valley are also excellent at absorbing and radiating heat. Much of the valley floor is covered with dark-colored rock and soil. These dark surfaces have a low albedo, meaning they absorb most of the sunlight that hits them rather than reflecting it. During the day, surface temperatures on dark rocks can reach 60 to 70 degrees Celsius, or even higher, hotter than the air itself. And even after sunset, the rocks remain warm enough to radiate significant amounts of heat throughout the night, keeping air temperatures elevated. It's common for nighttime temperatures in Death Valley during summer to stay above 35 degrees Celsius, which is uncomfortably warm by any standard. Despite these harsh conditions, Death Valley supports a surprising diversity of life. Over 1,000 species of plants grow here, each adapted to thrive with minimal water. The most common plant is probably the creosote bush, a remarkably hardy shrub that can survive on as little as 5 inches of rain per year. Creosote bushes have small, waxy leaves that minimize water loss, and they produce chemicals that inhibit the growth of other plants nearby, reducing competition for scarce water. The creosote is so well adapted to the desert that individual plants can live for hundreds of years, and clonal colonies, where new stems sprout from the root system of an old plant, can persist for thousands of years. Desert wildflowers appear in Death Valley during rare wet years, usually in late winter or early spring. The seeds of these annual plants can lie dormant in the soil for years, waiting for the right combination of rainfall and temperature to trigger germination. When conditions are right, the desert can briefly explode with color, carpets of yellow, purple, pink, and white flowers covering areas that are normally bare. These wildflower superblooms attract visitors from around the world, who come to witness the transformation of the harsh desert into a temporary garden. The flowers rush through their entire life cycle in just a few weeks, growing, flowering, producing seeds, and then withering before the summer heat arrives. Their seeds fall to the ground and wait, sometimes for many years, for the next favorable conditions. Death Valley is also home to numerous animal species, though you might not see them during the heat of the day. Bighorn sheep navigate the steep canyons and mountainsides, finding shelter in the rocks and feeding on sparse vegetation. Kit foxes, small and delicate-looking but remarkably tough, hunt during the cooler hours of dawn and dusk and throughout the night. Coyotes also roam the valley, adapting their schedules to avoid the worst heat. There are numerous species of lizards, including the collared lizard and the chuckwaller, which can tolerate higher body temperatures than most vertebrates. Snakes, including several species of rattlesnakes, are present but rarely seen, as they spend most of their time in sheltered areas and are primarily nocturnal during hot months. Even small fish survive in Death Valley, though this seems almost impossible. In scattered springs and small streams, you can find the devil's hole pupfish, one of the rarest fish in the world. This species has survived in a single limestone cavern with a small pool of warm water for thousands of years, adapting to extremely limited resources and high water temperatures that would be lethal to most fish. The entire population of devil's hole pupfish consists of just a few hundred individuals, making it one of the most endangered species on Earth, and an example of life's ability to persist in even the most unlikely places. But humans find Death Valley challenging. The few people who live and work in the valley have adapted their schedules around the heat. Outdoor activities happen in early morning or late evening. Air conditioning is not a luxury, but a necessity for survival. Buildings require constant cooling during summer months, which creates significant energy demands. Vehicles require special attention, as engines can overheat, and tires can fail on the superheated pavement. The asphalt itself can become soft and sticky in extreme heat, and tire pressure increases significantly, raising the risk of blowouts. Hikers are warned to carry enormous amounts of water, far more than they would need in moderate climates. The general recommendation is to drink at least 1 gallon of water for every 2 hours of activity, and even that may not be enough during the hottest part of summer. The human body loses water rapidly in such extreme heat through sweating, and dehydration can occur surprisingly quickly. Signs of heat exhaustion include dizziness, nausea, rapid heartbeat, and confusion. If not treated promptly by cooling the body and replacing fluids, heat exhaustion can progress to heat stroke, a life-threatening emergency where the body's temperature regulation system fails completely. Park rangers in Death Valley regularly deal with heat-related emergencies during summer months. Despite prominent warnings, some visitors underestimate the danger. They venture out on hikes without sufficient water, or they leave their vehicles and become stranded when the car won't restart due to overheating. Several people have perished in Death Valley over the years, victims of the extreme conditions. The Park Service has installed emergency call boxes at strategic locations and conducts regular patrols. But the vastness of the valley means that help may be hours away if someone gets into trouble in a remote area. Despite the challenges, or perhaps because of them, Death Valley has become a destination for a particular type of visitor. Adventure tourists come specifically to experience the extreme heat, to say they've been to one of the hottest places on Earth. Photographers are drawn by the dramatic landscapes, the interplay of light and shadow on the salt flats and mountains, the rare wildflower blooms, and the stark beauty of a land stripped to its essentials. Scientists come to study desert ecology, geology, and climate. And a surprising number of people simply find peace in the emptiness. In a landscape where the forces of nature are obvious and overwhelming, where human concerns seem small in comparison. The small community of Furnace Creek, one of the only permanent settlements in Death Valley, provides basic services for visitors and employs people to staff the national park facilities. The ranch at Furnace Creek has a golf course, which seems almost absurd in such a hot, dry environment. The course requires enormous amounts of water to maintain, drawn from underground springs that provide one of the few reliable water sources in the valley. The springs produce water at around 93 degrees Fahrenheit, too hot for most plants, so it must be cooled before it can be used for irrigation. Playing golf in Death Valley during summer, with temperatures exceeding 115 degrees, is an exercise in persistence and tolerance for heat. And yet, Death Valley has become a place people care about, protected as a national park, visited by over 1 million people annually, and the subject of ongoing scientific research. This harsh, extreme place has value precisely because it is harsh and extreme. It shows us what Earth can be like when conditions push to the edge of habitability. It reminds us that our planet is not uniformly hospitable, that there are still places that resist human domination and modification, that nature retains its power to create conditions we must respect and adapt to, rather than simply overcome. From Death Valley, let us journey briefly to Africa, to another place where heat defines existence, but where heat combines with other geological forces to create a landscape that seems almost alien, as if transplanted from another planet. In the Horn of Africa, where Ethiopia, Eritrea, and Djibouti meet, lies a geological wonder called the Danakil Depression. This is a place so extreme, so alien in appearance, that scientists come here to study what life might look like on other planets. Astrobiologists, researchers who study the possibility of life beyond Earth, are particularly interested in the Danakil Depression because its extreme conditions, high heat, high acidity, high salinity, might be similar to conditions on Mars or on some of the icy moons of Jupiter and Saturn, where liquid water might exist beneath frozen surfaces. The Danakil Depression sits approximately 125 meters below sea level, making it one of the lowest-lying regions on Earth. Only the Dead Sea shoreline in the Middle East and Lake Assal in Djibouti lie lower. The depression covers approximately 100,000 square kilometers, an area about the size of Iceland. It rests at the junction of three tectonic plates, the Arabian, Nubian, and Somalian plates. These massive slabs of Earth's crust, each thousands of kilometers across and up to 100 kilometers thick, are slowly pulling apart at a rate of about 1 to 2 centimeters per year. This might not sound like much, but over millions of years, this movement has opened a significant gap. The Danakil Depression is essentially a tear in the planet's surface, a place where the mantle beneath Earth's crust is closer to the surface than almost anywhere else. This has several consequences. First, volcanic activity is common because magma from the mantle can more easily reach the surface through the thinned crust. Second, heat from Earth's interior flows upward more readily, contributing to the already extreme surface temperatures caused by the sun. And third, the region is actively sinking and spreading, creating a dynamic landscape that's constantly, though slowly, changing. The result is a landscape of active volcanoes, lava lakes, and hot springs. The Erta Ale volcano, one of only a handful of volcanoes in the world with a persistent lava lake, sits within the depression. Erta Ale is a shield volcano, a type characterized by broad, gently sloping sides built up by fluid lava flows. Its summit crater contains a lava lake, a pool of molten rock that has been active continuously for over a century. At night, the lava glows orange and red, a window into Earth's molten interior. The heat from the lava is intense even at a distance, and the air above the crater shimmers and distorts from the rising heat. Standing at the rim of Erta Ale at night, watching the lava roil and spatter, is one of the most dramatic sights in nature. A reminder that our planet is not a dead ball of rock, but a dynamic, living world with a core that remains molten billions of years after its formation. The Dalol volcanic area, also in the Danakil Depression, features hot springs that create formations in vibrant colors, brilliant yellows, greens, and oranges caused by sulfur, iron, salt, and other minerals dissolved in the superheated water. The landscape around Dalol looks like something from a science fiction novel, with pools of acid water, mounds of crystallized minerals, and steam vents releasing sulfurous gases. The colors are astonishingly vivid, unlike anything you'll see in most natural settings. Bright yellow sulfur deposits contrast with green and brown iron compounds and white salt formations, creating patterns that seem almost painted rather than natural. These acid pools are some of the most extreme environments on Earth. The pH levels are extremely low, around 0 to 1 in some pools, meaning the water is as acidic as battery acid. Most organisms cannot survive in such conditions. Even the rocks and metals dissolve slowly in these acidic waters. Yet scientists have discovered microorganisms living even here, extremophiles that have evolved to not only tolerate but thrive in conditions that would be instantly lethal to most life. These organisms have proteins and enzymes that remain stable and functional in high acid and high heat. And studying them helps us understand the biochemical limits of life. But what makes the Danakil Depression particularly notable for our discussion is its temperature. This region holds the distinction of having the highest average year-round temperature of any inhabited place on Earth. The settlement of Delol recorded an average annual temperature of 34.6 degrees Celsius between 1960 and 1966. That's approximately 94 degrees Fahrenheit as an average, meaning that over an entire year, including winter months, the average temperature never drops below what most people would consider a hot summer day. That means, even in the coolest months, temperatures rarely drop below 30 degrees Celsius. In summer, daily highs frequently exceed 50 degrees Celsius, which is 122 degrees Fahrenheit. The combinations of heat and the volcanic landscape creates conditions that test human endurance. The air is often thick with sulfurous gases from the volcanic vents, making breathing difficult and unpleasant. The ground itself is hot to the touch in many areas, heated not just by the sun, but also by geothermal heat from below. Salt plains stretch for miles, bright white and flat, reflecting sunlight with intensity that requires eye protection. The glare from these salt flats can cause snow blindness, even though there's no snow, a painful condition where the cornea is effectively sunburned by reflected UV light. The Afar people, a semi-nomadic ethnic group, have lived in the Danakil Depression for generations. They are one of the toughest groups of people on Earth, having adapted their entire culture to survival in this extreme environment. The Afar mine salt from the vast salt flats that cover much of the depression, a trade that has continued for centuries. They cut blocks of salt from the ancient deposits, each block weighing about 4 kilograms. These blocks are loaded onto camels, with each camel carrying about 30 blocks, for a total load of around 120 kilograms. Now, having explored some of Earth's hottest places, let us shift our attention to the opposite extreme. Let us travel to landscapes where cold becomes the dominant force, where temperatures drop so low that exposed skin freezes within minutes, where the very air seems solid with chill. In the heart of Antarctica lies the coldest place on Earth. This frozen continent, nearly 1.5 times the size of the United States, is covered by an ice sheet averaging over 1 mile thick. Antarctica contains about 90% of the world's ice and more than 70% of its fresh water, all locked in frozen form. If all this ice were to melt, sea levels around the world would rise by more than 60 meters, redrawing coastlines and reshaping human civilization. The interior of Antarctica, particularly the high plateau that includes the South Pole, experiences temperatures so cold they seem to defy comprehension. On July 21, 1983, at a Soviet research station called Vostok Station, located deep in the interior of East Antarctica, thermometers recorded an air temperature of -89.2 degrees Celsius. That's -128.6 degrees Fahrenheit. This remains the lowest air temperature ever directly measured on Earth by ground-based instruments. To put this in perspective, -89 degrees Celsius is colder than the freezing point of carbon dioxide, which turns to dry ice at -78.5 degrees. At such temperatures, the moisture in your breath would instantly crystallize, forming tiny ice particles that would glitter in the air. If you were to breathe deeply, the cold air would cause immediate pain in your lungs and throat. Exposed skin would suffer frostbite within seconds. Any metal surface you touched with bare skin would instantly adhere, flash freezing the moisture on your fingertips. But even this extraordinary reading may not represent the absolute coldest temperature on Earth. Between 2003 and 2013, scientists analyzing satellite data from East Antarctica discovered something remarkable. In a high ridge region between two features called Dome Argus and Dome Fuji, surface temperatures during the polar winter dropped even lower than the Vostok reading. The satellites measured temperatures as low as -98 degrees Celsius, which is -144.4 degrees Fahrenheit. These satellite measurements record the temperature of the ice surface itself, not the air above it. The air temperature at these locations would be somewhat warmer, perhaps around -94 degrees Celsius, but still far colder than the Vostok air temperature record. These pockets of extreme cold occur under very specific conditions. The sky must be perfectly clear, allowing heat to radiate from the ice surface directly into space. The air must be extremely dry because water vapor acts as an insulating blanket, trapping heat near the surface. And these conditions must persist for several days, allowing temperatures to drop incrementally lower each night. Scientists believe that -98 degrees Celsius may represent close to the absolute coldest temperature possible on Earth's surface. To get colder would require conditions that simply don't persist long enough in Antarctica. The requirement for multiple consecutive days of clear skies and bone-dry air rarely aligns for long enough to push temperatures even lower. Why is Antarctica so cold? Several factors combine to create these extreme conditions. First, location matters. Antarctica sits at the South Pole, where the sun never rises high in the sky. Even during the Antarctic summer, when the sun circles the horizon without setting for months, the angle of sunlight is oblique. The sun's rays spread over a large area, never concentrating their heat the way they do in tropical regions. During the Antarctic winter, from March through September, the sun doesn't rise at all. The continent endures months of continuous darkness, with no solar energy arriving to warm the surface. Second, elevation plays a crucial role. Much of Antarctica's interior sits on a high plateau, with elevations exceeding 3,000 meters above sea level. At these heights, the air is thinner and holds less heat. The same atmospheric thinness that causes mountain peaks to be cold, even in tropical regions, makes Antarctica's high plateau extraordinarily frigid. Third, the ice itself contributes to the cold. Ice and snow are highly reflective. They bounce most of the sun's energy back into space rather than absorbing it. This property, called albedo, means that even when sunlight does strike Antarctica, it doesn't warm the surface much. Instead, the surface reflects up to 90% of the incoming solar radiation. Fourth, Antarctica's isolation matters. The continent is surrounded by the Southern Ocean and separated from other landmasses by hundreds of kilometers of water. Ocean currents circulating around Antarctica, particularly the Antarctic Circumpolar Current, effectively isolates the continent from warmer air masses. This creates a stable atmospheric pattern where cold air settles over the interior and stays there, with little mixing with warmer air from lower latitudes. The cold in Antarctica creates a landscape unlike anywhere else on Earth. The air is so dry that Antarctica technically qualifies as a desert, receiving less precipitation annually than the Sahara. Snowfall happens rarely. When it does snow, the flakes are tiny and hard, more like grains of sand than the soft flakes familiar in temperate regions. These tiny ice crystals blow across the surface in fierce winds, creating ground blizzards where visibility drops to zero, even though no snow is falling from above. The wind in Antarctica deserves its own discussion. Katabatic winds, driven by cold, dense air flowing down from the high interior plateau toward the coast, can reach hurricane force. The fastest wind speed ever recorded in Antarctica was 327 kilometers per hour, measured at Dumont d'Urville Station in July 1972. These winds don't just blow, they roar and scream, driving ice particles with such force that they can strip paint from buildings and polish exposed rocks to a glassy smoothness. Living in Antarctica, is one of the most challenging endeavors humans have attempted. Research stations dot the continent, hosting scientists who study everything from climate change to astronomy to the biology of extremophile organisms. These stations are marvels of engineering, designed to provide warmth, air, water, and power in an environment where none of these things occur naturally. Buildings are raised on stilts to prevent them from being buried by drifting snow. Multiple layers of insulation and sophisticated heating systems work continuously to maintain livable interior temperatures. Windows are triple-paned, and entranceways have multiple doors to create airlocks that prevent heat loss. The people who winter over in Antarctica, those who stay through the dark months when no planes can reach the continent, describe the experience as both isolating and transformative. The darkness weighs on you after weeks without sunlight. The cold is always present, always waiting for any mistake that might allow it inside. The tiny community becomes everything. Your colleagues the only other humans in a radius of thousands of kilometers. Yet many who experience Antarctic winter return again and again, drawn by the raw beauty, the stars that blaze with impossible brightness in the dry, clear air, the aurora australis dancing in curtains of green and purple across the sky, and perhaps most of all, by the profound sense of being in a place utterly unlike anywhere else. But Antarctica is not the only place on Earth where extreme cold shapes existence. Let us travel now to the northern hemisphere, to a region of Siberia where people have chosen to make their homes, despite temperatures that regularly plunge below -50 degrees Celsius. In eastern Siberia, in the Sakha Republic of Russia, two small settlements compete for the title of the coldest permanently inhabited places on Earth. Their names are Oymyakon and Verkhoyansk, and both have recorded temperatures below -67 degrees Celsius. Oymyakon is a rural village situated in a valley along the Indigirka River, approximately 750 meters above sea level. The name comes from an even word that may mean unfrozen patch of water, or possibly frozen lake, depending on the source. Either interpretation speaks to the complex relationship between this place and ice. In February 1933, Oymyakon recorded a temperature of -67.7 degrees Celsius. A monument in the village square commemorates an even lower unofficial reading of -71.2 degrees Celsius, allegedly measured in January 1924, though this number has never been officially verified. Verkhoyansk, located on the Yana River, about 629 kilometers from Oymyakon, shares similar conditions. In February 1892, thermometers there recorded -67.8 degrees Celsius. For decades, these two communities have held a friendly rivalry over which can claim to be coldest, with the difference between their record lows being merely 1/10 of a degree. But here's what makes these places truly remarkable. Unlike the research stations in Antarctica, which host scientists who rotate in and out, Oymyakon and Verkhoyansk are home to permanent populations. Around 500 people live in Oymyakon, and about 1,300 in Verkhoyansk. These are people who have chosen to build lives in conditions that seem almost designed to be inhospitable to humans. What is daily life like in a place where winter temperatures regularly drop below -50 degrees? It requires constant vigilance and adaptation. Vehicles must be kept running almost continuously during the coldest months, because if an engine is shut off, it may never start again. The oil becomes too thick to circulate, batteries lose their charge, and metal parts can crack from the extreme temperature. Many residents keep their vehicles in heated garages, or, if parking outside, leave the engine running all day while at work and all night while sleeping. Buildings are constructed with multiple layers of insulation, often using materials like reindeer fur between walls. Windows are small and triple glazed. Heating systems burn constantly, fed by wood, coal, or fuel oil. Running water is rare, because pipes freeze even when insulated and buried deep underground. Many homes rely on outhouses rather than indoor plumbing. And yes, using an outdoor toilet when it's -60 outside is as unpleasant as you might imagine. Food preservation is simple. The entire outdoors functions as a freezer. Fresh meat can be stored outside for months without spoiling. Fish caught through holes in river ice freeze solid within minutes and can be stacked like cordwood. Vegetables are precious and expensive, brought in from distant cities at great cost. Clothing becomes armor against the cold. People dress in layers upon layers, starting with thermal underwear, adding wool sweaters and pants, then covering everything with parkas made of thick fur. Hats, gloves, scarves, and face masks are essential. Even with all this protection, spending more than 15 or 20 minutes outside during the coldest days is dangerous. Frostbite can occur in seconds on exposed skin. Children stay home from school only when temperatures drop below -52 degrees Celsius, a threshold that speaks to the remarkable hardiness of the people who live here. Yet these communities have existed for generations. The indigenous Yakut people have lived in this region for centuries, developing strategies to survive the cold that have been passed down through countless generations. They rely on reindeer herding, hunting, and fishing, activities that require being outside, even in the worst conditions. Their traditional knowledge includes understanding how animals behave in extreme cold, how to recognize the early signs of frostbite, which plants have medicinal properties useful for cold-related ailments, and how to navigate safely when daylight lasts only a few hours each winter day. Interestingly, these same places that suffer through winters of unimaginable cold experience relatively warm summers. In July, temperatures in both Oymyakon and Verkhoyansk can exceed 30 degrees Celsius. Verkhoyansk holds a particularly extraordinary record for having the greatest temperature range on Earth. The difference between its all-time high of 38 degrees Celsius, recorded in June 2020, and its all-time low of -67.8 degrees, produces a range of 105.8 degrees Celsius. Imagine living in a place where the thermometer can span from -67 to +38. Your body, your home, your entire life must be prepared for both extreme cold and summer heat. This dramatic temperature swing occurs because of the region's distance from any ocean. Water has a high heat capacity, meaning it warms and cools slowly. Coastal areas benefit from this ocean moderation, rarely experiencing extreme temperatures in either direction. But the interior of Siberia, thousands of kilometers from the nearest ocean, has no such buffering. The land heats quickly under the summer sun and cools rapidly when winter darkness descends. Add to this the high latitude, where the sun stays below the horizon for much of winter, but circles the sky without setting for much of summer, and you create conditions for wild temperature extremes. Despite the hardships, the people of Oymyakon and Verkhoyansk express pride in their communities. They celebrate their status as the coldest inhabited places on Earth. Festivals are held in winter, featuring traditional ice sculptures, reindeer races, and games played on frozen rivers. Tourists have begun visiting, drawn by curiosity about how people can live in such extreme conditions. These visitors find not a land of suffering, but communities that have adapted, that find beauty in winter landscapes of pristine white snow and ice, and that possess a resilience forged by necessity. From Siberia, we might briefly visit other cold places. The summit of Greenland's ice sheet, rising nearly 4,000 meters above sea level, experiences brutally cold conditions year-round. The coldest temperature ever reliably measured in Greenland was -69.6 degrees Celsius at an automatic weather station in December 1991. The Yukon and Alaska have their own regions of severe cold. International Falls, Minnesota, and Duluth, Minnesota, in the United States, regularly experience winter temperatures dropping below -30 degrees. Fort Yukon, Alaska, has recorded temperatures as low as -60 degrees. But none of these places quite compare to the two extremes we've explored in depth. The endless ice desert of Antarctica, where the planet itself seems to reach its absolute limit of cold, and the Siberian valleys, where humans have chosen to make permanent homes despite conditions that challenge every aspect of survival. Let us pause here and consider what these temperature extremes mean for Earth as a whole. Our planet exists in what scientists call the habitable zone around our Sun, not too close to be scorched like Venus, not too far to be frozen like Mars. Earth's average surface temperature hovers around 15 degrees Celsius, a temperate middle ground that allows liquid water to exist, and where liquid water exists, life can thrive. But these extremes remind us how thin the margin of habitability really is. The difference between the hottest and coldest temperatures naturally occurring on Earth spans about 190 degrees Celsius, from around +80 in the Lute Desert to -98 on Antarctica's high plateau. That's a range of over 340 degrees Fahrenheit. Humans, with our narrow range of thermal comfort, typically feel best between roughly 15 and 25 degrees Celsius. Step outside this range, and we quickly become uncomfortable. Go much further, and we face serious danger. The study of these temperature extremes teaches us about Earth's climate system and how energy moves around our planet. Heat travels from hot regions to cold regions, driven by winds and ocean currents. These flows of energy determine weather patterns, influence where rain falls and deserts form, and govern which species can survive where. Understanding extreme temperatures also helps scientists predict how climate change might alter these patterns. The world is warming. Global average temperatures have risen by roughly 1 degree Celsius since pre-industrial times, and the warming continues. This might not sound like much, but remember that we're talking about global averages. Some regions are warming much faster than the average, particularly in the Arctic, where temperatures are rising at more than twice the global rate. Antarctica, too, is changing, with ice sheets beginning to melt in some coastal areas. These changes affect the extreme temperature records we've discussed. The possibility of seeing new record high temperatures becomes more likely with each passing year. Death Valley, the Lute Desert, the Danakil Depression, all may see even higher readings as the atmosphere warms. Meanwhile, the frequency of extreme cold events in places like Siberia may decrease, though Arctic cold snaps can still occur when atmospheric circulation patterns shift. Scientists monitor these changes carefully. Weather stations scattered across the globe, satellite measurements from space, and sophisticated computer models all contribute to our understanding of how temperature patterns are shifting. Data reveal a world in transition, where the familiar climate patterns that have existed throughout human history are beginning to change in ways both subtle and profound. But tonight, as you rest, you need not worry about these large-scale concerns. Instead, let your mind find peace in the simple wonder of Earth's diversity. How remarkable that our planet contains such contrasts, such extremes. How extraordinary that matter behaves so differently at these temperature boundaries. How impressive that life has found ways to exist even in the hottest deserts, and that humans have chosen to inhabit even the coldest valleys. Think of the Lut Desert at midday, the air shimmering with heat, the sand too hot to touch. Then imagine Antarctica at midnight during winter, the stars impossibly bright in the black sky, the cold so complete that it seems solid. These places exist simultaneously on our shared world. While the Lut Desert bakes, Antarctica freezes. While people in Oymyakon bundle in furs against -60-degree temperatures, tourists in Death Valley marvel at thermometers reading +50. Our planet is large enough, diverse enough, complex enough to contain all of these realities at once. Mountain peaks near the equator hold glaciers, while nearby lowlands swelter under tropical sun. Ocean currents carry warmth from the equator toward the poles, then return cold water back toward the tropics. The atmosphere circulates in great cells, rising at the equator where heat makes air buoyant, flowing poleward at high altitude, then sinking in the subtropics to create the world's great deserts, before flowing back toward the equator as surface winds. All of this movement, all of this energy transfer, all of these atmospheric and oceanic currents, they exist to balance the uneven heating of our planet. The sun warms the equator more than the poles, and Earth systems work constantly to redistribute that heat. Weather is the short-term manifestation of this redistribution. Climate is the long-term pattern, and the extremes we've explored tonight are the outliers, the places where the normal patterns break down and create conditions so far outside the average that they seem almost alien. Yet, even in these extreme places, beauty persists. The Lut Desert's yardangs, those massive wind-carved ridges, create landscapes that could grace a science fiction novel. The Danakil Depression's acid springs paint the ground in colors so vivid they seem artificial. Antarctica's ice formations, carved by wind into shapes called sastrugi, catch the low polar sunlight and glow with shades of blue and white and pink. The winter landscapes of Oymyakon and Verkhoyansk, blanketed in pristine snow, lit by the pale sun that barely rises above the horizon, possess a stark beauty that visitors struggle to describe adequately. Humans have always been drawn to extremes, to the edges of experience, to the limits of what is possible. We climb the highest mountains, dive to the deepest ocean trenches, and venture into the hottest and coldest places. Partly this is curiosity, the desire to know, to understand, to measure, and catalogue. Partly it is challenge, the human need to test ourselves against difficult conditions. And partly it is wonder, the simple awe we feel when confronting nature at its most extreme. The stories of people who live and work in these extreme environments are stories of human adaptability. The Afar people mining salt in the Danakil Depression under 50-degree heat. The scientists maintaining research stations in Antarctica through the long polar night. The residents of Oymyakon and Verkhoyansk, raising families, attending school, going to work, living full lives in conditions that would send most of us scrambling for milder climates. These are testaments to human resilience and ingenuity. But equally important are the lessons these places teach about respect for nature's power. Heat and cold at these extremes are not to be taken lightly. They demand careful preparation, proper equipment, and constant vigilance. Mistakes that might be minor annoyances in moderate climates become life-threatening in extreme temperatures. Running out of water in Death Valley can be lethal within hours. Getting lost in an Antarctic blizzard means almost certain demise. Even in inhabited places like Oymyakon, carelessness during the coldest days can lead to severe frostbite or worse. Yet people continue to visit these places, to study them, to marvel at them. And in doing so, they return with a deeper appreciation for the more moderate climates where most of us live. The next time you feel uncomfortably warm on a summer day, remember that you're not facing 50-degree heat in Death Valley. The next time you shiver on a winter morning, remember that you're not experiencing minus 60 degrees in Oymyakon. Our everyday temperatures, the ones we often complain about, exist in a remarkably comfortable range. Earth's temperature extremes also remind us of our planet's place in the solar system. Mercury, closer to the Sun, experiences temperatures ranging from minus 170 degrees Celsius on its night side to over 400 degrees on its day side. Venus, with its thick atmosphere trapping heat, maintains surface temperatures around 460 degrees Celsius everywhere, hot enough to melt lead. Mars, farther from the Sun and with a thin atmosphere, averages around minus 60 degrees, though temperatures can range from minus 125 in winter at the poles to plus 20 near the equator in summer. Jupiter, Saturn, Uranus, and Neptune, the gas giants farther out, experience conditions so extreme that temperature becomes difficult to even define, with crushing pressures and exotic states of matter. Earth, by comparison, is gentle. Our extremes, as dramatic as they seem to us, are narrow. The difference between our hottest and coldest natural temperatures is large from a human perspective, but tiny on a cosmic scale. And most of our planet exists in the temperate zone between these extremes, with conditions suitable for liquid water, comfortable for life, and stable enough to allow for the complexity that gives us forests and grasslands and coral reefs and all the biological diversity we cherish. As your breathing slows and your mind begins to drift towards sleep, let these images settle into quiet contemplation. Picture the vast emptiness of the Lut Desert, silent under a blazing sun. Imagine the endless white of Antarctica, a continent of ice larger than Europe, where human presence is tiny and temporary. Think of the resilient people of Siberia, going about their daily lives, while thermometers read temperatures that would send most of us fleeing. Consider the strange beauty of the Danakil Depression, where Earth's interior heat rises close to the surface and creates landscapes unlike anywhere else. These places exist. They are real locations on the same planet where you rest comfortably tonight. The same atmosphere that delivers gentle breezes to your window also carries the heat of the Lut Desert and the cold of Antarctica. The same sun that warms your face on a pleasant spring day also beats down mercilessly on Death Valley and barely grazes the horizon in an Antarctic winter. Our world is vast and varied. It contains multitudes. It holds within it every condition, from the incomprehensibly hot to the unimaginably cold. And somewhere in the middle of this range, in the temperate zone where water flows and plants grow and life flourishes, there is a bed where you lie, comfortable and safe, ready for rest. You do not need to survive in Death Valley's heat or Antarctica's cold. You do not need to test yourself against these extremes. Others have done so, and their experiences teach us what is possible and what is worth risking. You need only appreciate that such places exist, that Earth is complex enough and large enough to contain them, and that the universe has provided us with a planet diverse enough to inspire endless wonder. The hottest and coldest places on Earth are extremes, outliers, places that push the boundaries of what seems possible. But they are also part of the beautiful whole, part of the intricate system that makes Earth the vibrant, living world it is. Heat and cold drive winds and currents. Winds and currents distribute moisture and nutrients. Moisture and nutrients support life. Life, in turn, modifies the atmosphere and the surface, participating in the grand cycles that keep our planet habitable. Everything connects. The Lut Desert's heat contributes to atmospheric circulation patterns that affect weather thousands of kilometers away. Antarctica's ice sheets reflect sunlight back into space, helping to regulate global temperatures. The lessons learned from people surviving in Oymyakon's cold advance our understanding of human physiology and adaptation. The microorganisms discovered in the Danakil Depression's acid springs give us insights into how life might exist on other worlds. Nothing exists in isolation. Everything is part of the whole. And you, resting tonight, are also part of this whole. You are made of elements forged in ancient stars. You breathe air that has cycled through Earth's atmosphere for billions of years. You drink water that has fallen as rain and snow, flowed through rivers, evaporated from oceans, and repeated this cycle countless times. You exist in the comfortable middle of Earth's temperature range, the zone where humans evolved and where we thrive. The study of extremes helps us understand the average. By examining the hottest and coldest places, scientists learn how heat moves, how cold persists, how life adapts or struggles. This knowledge informs everything from weather forecasting to climate modeling to the search for life on other planets. If microorganisms can survive in the Lut Desert's heat or Antarctica's cold, what might survive in the apparently harsh conditions on Mars or the icy moons of Jupiter and Saturn? But beyond the scientific value, beyond the practical applications, these extreme places serve another purpose. They inspire awe. They remind us that Earth is not uniform, not predictable, not entirely tamed. They show us that nature retains its power to surprise, to challenge, to exist in forms we find difficult to comprehend. This sense of wonder is valuable in itself. It keeps us humble, keeps us curious, keeps us aware that despite all our knowledge and technology, the natural world still holds mysteries and extremes that command our respect. Tonight, as you settle into sleep, you can release all effort and worry. You need not brave extreme heat or extreme cold. You need not mine salt in the Danakil Depression or maintain equipment through an Antarctic winter. You need not drive across frozen rivers in Siberia or hike through Death Valley in summer. Others have done these things, and their experiences add to humanity's collective understanding. You need only rest. Let your muscles relax, starting with your feet and moving up through your legs, your torso, your arms, your neck and face. Release the tension you may not even realize you're holding. Breathe slowly, deeply, naturally. There is no effort required, no task to accomplish. Sleep will come in its own time, gentle and inevitable as the sunset. Your mind may wander for a while longer, perhaps revisiting images from tonight's journey. The shimmering heat of the Lut Desert, the pristine white silence of Antarctica, the colorful acid springs of the Danakil Depression, the frost-covered buildings of Oymyakon. These are places you may never visit in person, but through the power of imagination and description, you've traveled to them tonight. You've stood in the hottest and coldest places on Earth, at least in your mind's eye. And now, having made that journey, you can return home. Return to your comfortable bed, your moderate temperature, your safe and familiar surroundings. The extreme places will still be there, doing what they do, existing as they have for thousands or millions of years. The Lut Desert will continue to bake under the summer sun. Antarctica will continue to freeze in the winter darkness. And somewhere in the middle, in the temperate zones where most humans live, you will continue to rest and wake and live your life. The beauty of Earth is not just in its extremes, but in its entirety. The whole spectrum, from hot to cold, from wet to dry, from low to high, from barren to lush. Every part contributes to the whole. Every place has its role in the larger system. And every temperature, from the scorching heat of the Lute to the bone-chilling cold of Antarctica, is part of what makes Earth the complex, dynamic, living planet that we call home. As your thoughts become gentler, less focused, more like dreams than waking contemplation, let yourself appreciate the simple gift of comfort. You are neither too hot nor too cold. You are just right. The temperature around you is suitable for rest. The surface beneath you is soft. The air is calm. All is well. There is nothing you need to solve tonight. No problem requires your attention. No decision awaits. The world will continue spinning. Temperatures will continue varying. The sun will rise and set. Winds will blow. And all of Earth's systems will carry on without any effort from you. Your only task is to rest. Your only goal is sleep. And so, having traveled to the ends of Earth's temperature range, having visited deserts and ice fields, having learned about people who thrive in conditions that seem impossible, you can now release all of this. Let the knowledge settle into your memory, like sand filtering down through water. Some details will remain clear, others will blur, and that's perfectly fine. You don't need to remember everything. You don't need to hold on to anything. Just let go. Let your breathing slow further. Let your body sink deeper into rest. Let your mind drift free, no longer bound by logic or narrative or the need to pay attention. Sleep is coming, gentle and sure, like night following day, like winter following autumn, like cold following heat and heat following cold. It's a natural cycle, and you are part of it. The hottest and coldest places on Earth will still be there tomorrow. The Lute Desert will still shimmer in the heat. Antarctica will still glitter with ice. Oymyakon will still endure its winter cold. Death Valley will still bake in summer sun. These extremes are constants, the edges of Earth's temperature range, the boundaries that help define what is possible on our planet. But you do not live at the extremes. You live in the comfortable middle, where life is easiest, where humans have always thrived. And right now, in this moment, you rest in exactly the right place, at exactly the right temperature, ready for sleep. You have traveled far tonight in your imagination. You have learned about places most people never see, conditions most people never experience. And now your journey is complete. You have reached your destination, which is simply here, now, rest. Let everything else fall away. The deserts, the ice sheets, the cold valleys, the hot springs, all of it can wait. None of it needs you. The universe is unfolding as it should, temperatures rising and falling in their endless cycles, heat flowing from warm to cold, energy redistributing itself across the planet's surface, all without any effort or attention from you. You are free, free to rest, free to sleep, free to release the day and embrace the night. The extremes of temperature are fascinating, but you don't need to experience them. You need only appreciate that they exist, that Earth is complex enough to contain them, and then let that appreciation dissolve into the gentle darkness of sleep. Your breathing is slow now, steady and calm. Your body is relaxed, heavy with the pleasant weight of approaching sleep. Your mind is quiet, thoughts becoming softer and more scattered, no longer following clear paths, but instead wandering into the dreamlike territory that precedes true sleep. The hottest place and the coldest place on Earth, they are just labels, just extremes, just interesting facts in the vast encyclopedia of knowledge about our world. What matters more, what matters most, is that you are comfortable, safe, and ready for rest. And so, let this be your final thought before sleep takes you. Earth is a good home. It has extremes, yes, but most of it exists in the gentle middle where life flourishes. You are fortunate to live in this middle ground, where temperatures allow comfort, where seasons change, but rarely to extremes, where the challenges of heat and cold are manageable rather than overwhelming. You have done enough thinking for tonight. You have learned enough, wondered enough, traveled enough in your imagination. Now it is time to simply be, to rest, to sleep. Let the extremes fade from your mind. Let the heat and cold become distant abstractions. Let everything dissolve into the warm, comfortable darkness of sleep. Good night. Rest well. Dream peacefully if you dream at all. And know that tomorrow, when you wake, the world will still be here, still turning, still maintaining its beautiful complexity. But tonight, none of that requires your attention. Tonight, you need only sleep. Close your eyes if they're not already closed. Release any remaining tension. Breathe, rest, sleep. The journey is over and you are home. Everything is exactly as it should be. And you are enough. You have done enough for today. Now rest. Sweet dreams.